Hello and welcome back to another video. This one will be introducing ensembles of decision trees. If you are not familiar with decision trees by themselves, I recommend going back and checking my last video where I introduced decision trees, because in this video we're talking about ensembles or groupings of decision trees. Okay, so with that said, ensembles of decision trees are often referred to as random forests. That may be a term that most folks are more familiar with. It's a more popular term used, and it's a concept that is used to address one of the bigger problems of decision trees, as powerful as they are already. And that problem is decision trees have this tendency of overfitting. If you watched the last video, it's fine if you didn't, but the idea where a decision tree can easily overfit is because if we don't have any kind of constraints on the depth of the tree, then depending on the kind of data that we have, it's very possible that the amount of decisions or tests that a decision tree is going to make, it can just go on and on and on forever, which will essentially make tons of different changes to the decision boundary of your decision tree, such that it gets 100% training accuracy. But when your decision boundaries, let's draw a little example very quickly. So we have two classes of data points. We have some yellow ones spread throughout, and we have some green ones also spread throughout. Okay, now you can see that there's a little bit of overlap between these two classes, and a decision boundary that we want to see may look something like this, right? But you can see there are a couple points that are still misclassified in this approach. And so a decision tree, again, if we don't have any constraints on it during training, can actually look a lot worse. So let's redo this here. And let's say it looks something like this. Very, very tight tolerances. Right? And then you see some more decision boundaries that pop up. Right? And the moment a new yellow data point comes in, it could very easily be in a location like here or here, right? And this starts to ruin our generalization ability, our testing performance. And so we want to avoid overfitting our models so that they look like this. And so that's where random forests come in to save the day. So the solution here is to, instead of having one decision tree, you're creating many trees, and you're randomizing the training process. And so that once you have an ensemble of decision trees, you can take their collective results in their predictions, average them per se, and use that collective effort to arrive at a more confident decision and result. Okay, so we'll talk a little bit about the process here, and there's a couple different aspects of the randomization when it comes to random forests. The first one is we take bootstrap samples of the data. And so if you look right here, let's say that you have some number of data samples. We have a data point A, data point B, data point C, data point D. And what we do is that for each tree, we take a bootstrap sample of it, where we take we sample a number of randomly selected data points with repetition. So that's why you can see a D here and a D here, or a D here and a D here. And although on the individual level, not every tree will see the entire data set. As a matter of fact, on average, about 1/3 of the data set is left out on each tree. But because or actually, when you have several trees and more trees and larger trees, I'll talk a little bit later how more trees tends to perform better, then you'll gradually have more coverage of the entire data set. But the idea here is that every tree is going to see a different subset of the data, such that each tree trains differently, so you can have different results. And the more different your results are, once you average them all together, then you'll have a much more confident result. that your tree arrives at. So the explanation here, a tree is trained from a bootstrap sample, but instead of the training algorithm finding the best tests, it takes a subset of the features. This is actually the second randomization aspect of decision trees. So we're taking a subset of the features and find the best tests that involve those features. So it's very similar to how I described here, how you can have the same data point occurring multiple times, but you don't have other aspects factored in to the training that's done on this set, for example. Like B is missing from here. So the tree that trains off of this data set will not have this B data point in here. Let's clean that up a little bit. Okay? So again, this second aspect is by doing or selecting a subset of the features as opposed to selecting a subset of the data points themselves. And what this does is a very similar effect where each tree is going to put a different weight or importance on different features. So say, for example, on my last video, I talked about how a single decision tree can place a lot of importance on a single feature. You might have 30 features, but one of them may just be absolutely dominant in the prediction process, right? But in our ensemble of trees, we actually leave out that super important feature. So then we may discover that there is another feature that can be critically important, right? And so once we have this growing random forest, we have different feature importances that also we can use for analysis to figure out what is the true distribution, what is the true importance of features. So this is mixed in with our randomization of the data selection. So two major aspects are at play. These are the two big speakers or top dogs when it comes to these decision trees, these ensembles of decision trees, these random forests. We have the bootstrap samples from the data selection, and then we have a randomized feature selection. So the idea is that these two mechanisms of randomization ensure that each tree is going to have something different, something unique to bring to the table that makes our predictions just that much better. So there's another critical parameter, we'll call it. It's called max features. And the idea here is you're selecting the number of features that, you're selecting the number of features that will be in these subsets when you do this randomized feature selection. So again, you may have a data set that has 30 different features, but when we do this randomized feature selection, we only take 20 of the 30, or 10 of the 30, 15 of the 30. That number is determined by max features, right? And the property of max features that you want to be aware of is that as max features approaches the number of features, so again, we'll take the example of having 30 features. As max features approaches 30, we'll see that there's actually little randomness, because let's say if max features was 29, that means every single tree will see 29 out of 30 features, meaning there's a lot of overlap from tree to tree. Right? At most, you have one different feature between any two trees. So this actually reduces the randomness of your random forest because each tree is seeing the same features. So let's go in the other direction. Max features now approaches 1. It gets smaller. Let's say we take 5 out of the 30 features. Right? This means each tree is going to be different because you may have as many as 5 or 6 trees that will not have any features in common, but they're all going to be making predictions on data that comes from the same original set. Right? And because in that case it's fair because the data is the same, but we're just looking at different features. These trees are going to get way different results likely, and once we average it all together, we get a much better understanding, our model gets a much better understanding of the data and its predictive abilities. And one other thing to note here is that when max features is low, close to 1, then trees will tend to be deeper to fit their data, because since you're only given now, take this example, 5 out of the 30 features, then you can't rely on the features to make as accurate of a prediction as possible. And so the tree is going to have to learn different tests in a deeper amount or a deeper tree, so it can have more tests in order to fit that data as well as it can. So that's how the training process works. And if we talk about the predictions, the predictive ability, every tree is going to make a prediction. The same way you have a single decision tree, every tree in this ensemble is going to be making different predictions. Ensemble trees, just like basic decision tree, can be used for both regression and classification. And when it comes to regression, the prediction is just simply averaged. If you have a numerical output, every tree will probably have a different numerical output, so it will just be averaged together to get your prediction. For classification, where random forests tend to stand out, where they gain their popularity, the predictions are grouped together. So if you had 100 trees, every tree makes a prediction of, let's say, 3 different possible classes that a data point can belong to. And essentially, of those 100, let's say 70 of them choose class 1, 20 of them choose class 2, and 10 of them choose class 3. Well, most of them picked class 1, so this data point, once we factor in all the trees' results together, we're going to say it's class 1. And wrap up here, we'll talk a little bit about some strengths and weaknesses of these ensembles. Remember, so basically, the ensemble of trees is better than a single tree. In almost every case, almost every scenario, ensemble of trees is better because you're taking the same information, but you're essentially just multiplying it. Take the same information, generating different conclusions off of it. It's like if you have one person being the leader of an organization versus an entire board or an entire executive suite that can talk things out and rationalize and bring new ideas to the table so you can arrive at a better solution, a better decision that is made. Okay? So the strengths and weaknesses, first up, is that ensembles of trees, as powerful as they are, taking advantage of many, many, many decision trees, they require only a little bit of hyperparameter tuning, if at all. The 3 ones I alluded to throughout this video, thing I have down here, the number of estimators, that is your number of trees. So again, we start with 1 decision tree, but we can have 50, we can have 100, thousands, tens of thousands. A good rule of thumb is basically to make as many trees as your computer can accommodate for. As much time and memory that you can factor in is how many trees you should have. The max features, the number of features that are used in this subset of features, again, if it approaches the total number of features, then if it approaches the total number of features, then each tree isn't really having a lot of randomization compared to the other trees. But if it approaches 1, then you're going to have much, much deeper trees, which can take more time to train or require more memory to instantiate on your system. So you have to find a balance there. The last one is a pruning technique, max depth. It's another parameter that can be used if you're using the sklearn machine learning library. But the max depth is basically if you want to set a maximum depth for all your trees in your ensemble, just so they're not too deep. It's just another parameter that you can use that may affect your training times. It may affect your prediction accuracies. Just another tool that you can toy around with. Second up is that you can parallelize with multiple CPU cores. Each tree is trained independently. Once you have your data set partitioned as you want it to be and your feature subsets selected, then who's to say that one tree can spend time training on one core of your processor and another tree can train on a different core of your processor. All right, so if you are someone who has a beefy, powerful computer available to you, you can take advantage of all that processing power so that your training and prediction times can hopefully be reduced. Random forests set different states. This makes reproducibility pretty difficult. The book here talks a little bit about if you want to if you want to be able to present analytics of your random forest to an audience, for example, the information can get pretty complex, especially when you have the properties of one tree multiplied times 1,000 for 1,000 trees. Right? So something to keep in mind if that matters to you, if reproducibility doesn't matter, you just want to get the best testing accuracy possible, this isn't something that you need to worry too much about. Next up here, random forests. They do not perform well on high dimensional data or sparse data. That is because if you don't have a lot of information, then it becomes difficult to train. Again, you can make up for this if you, again, it's a random forest, so more trees is more information based off of however many data points that you do have. Okay. They're also slow to train and predict. These trees can be very deep. They can have a lot of different decisions to make or tests to evaluate, and you also have a very large number of these. So if you look back at the k nearest neighbors algorithm, for example, you're iterating a couple times over the entire data set, but at most your big O or your complexity of that algorithm is going to be some factor times the number of data points. Right? You iterate over the data point 2, 3, 4, 5 times. But when it comes to random forests, you're iterating over the entire data set for every single tree for as many levels of the tree. Right? So deeper trees, lots of data, lots of features to factor in for. It takes more time. So if you have an application that requires a real-time speed or low storage power, if you need this to run on like a Raspberry Pi or something, this is a constraint that you may have to deal with when you're solving your problem. Okay, so last of all, large models perform better when it comes to random trees. That's why, or random forests. That's why this concept exists in the first place, because a forest performs better than a tree. Again, the easy way to understand this is that you have a certain amount of data that you can train one decision tree based off of. But if we take that same amount of data, meaning that we're not introducing any new information to our problem, we take that same amount of data and then partition it and train on multiple trees. This is our way of introducing new information, new insights to the problem without having to change any of the dimensions or parameters of the problem itself. We're using the same information and just generating more insights off of it. So I hope that helps you out. I hope this was a good introduction to ensembles of decision trees and random forests. If you have any feedback you would like to leave in the comments, please absolutely feel free to do so, whether I did a good job or an absolutely terrible job. If you want me to remake the video, just go ahead and say so, and if there's enough demand, I may actually do it. So with that, hopefully this video helped you out. Have a great day, and looking forward to catching you on the next video. Take it easy.